In this video we're going to look at how to form inverse functions, and we'll also have a quick look at their graphs as well, but that will also be the next lesson. So we're going to look at this function machine here. So we've got f of x is equal to 3x minus 1, and then the next part of the machine we've got g of x equals x plus 1 all over 3. Now the input to the first machine is x equals 5. Okay? So I want to find f of 5 here. So f of 5 is the same as 3 times 5 minus 1, which is 15 minus 1, which gives us 14. So 14 is the output of the first machine there, but also the input of the second one. So I've now got g of x is equal to x plus 1 all over 3, and I want to find g of 14. So 14 plus 1 all over 3 is 15 over 3, which is equal to 5. So we can see here that g of f of 5 is equal to 5. And you might have already noticed that the input was 5 and the output is also 5. And that's why it's g of f of 5 equals 5. And because the input and the output are the same as each other, we have inverse functions. So f is the inverse of g, and g is the inverse of f. Let's look at this more generally. So say my input was just x. So I know if I put x into f of x, I'm going to still have 3x minus 1. And now my input to g is 3x minus 1. So g of 3x minus 1, remember everywhere in g where there's an x, I'm replacing that with 3x minus 1. So 3x minus 1 plus 1 all over 3. So 3x minus 1 plus 1 gives me 3x over 3 gives me x. And again, you can see here that my input was x and my output was x. So because g of f of x is equal to x, that means that g and f are inverses of each other. So let's just explore this a bit more. Inverse functions reverse each other. They do the opposite of each other. They're opposites, they are inverses. If a function is defined on a suitable domain, then it will have an inverse function. And finally, the domain of an inverse function is the range of the original function and vice versa. So I'll say that again. The domain of an inverse function is the range of the original function and vice versa. So the range of the original function here was 3x minus 1, and that was the domain of the inverse function. Let's have a look at an example. So a function f is defined for all real numbers by f of x equals x cubed plus 1. Find a formula for its inverse, and the inverse is denoted by f to the power negative 1. So the inverse of f. So the solution, now I'm going to go through two methods for this. So I'll do the first method, you can copy that down, and then I'll do the second method. You can copy that down so that you've got them both in your notes, and then you can come back and decide which you would prefer to use, which is easiest for you. So we start by saying let y equal f of x. which implies then that x is equal to the inverse of f of y. Now remember, that comes from the fact that y is the range of the original function, but the domain of the inverse function. And likewise, x is the domain of the original function, but the range of the inverse function. So on the previous slide I talked about the domain and range and the effects that has on the original and the inverse function, or sorry, the effects that the original and the inverse function have on the domain and range, other way around. So you can see it here and coloured it for you so that it makes it more obvious. Now if we just let y equal f of x, now currently f of x is equal to x cubed plus 1. So that must mean that y is equal to x cubed plus 1. Now I want to rearrange this so that I get x. So I want x to be the subject of the formula. So I want to subtract 1 from both sides. So y minus 1 equals x cubed. And in order to get x, the subject of my formula here, I need to cube root both sides. So x is equal to the cube root of y minus 1. Now I know that x is actually equal to the inverse of f of y, and I've got x here, so that must mean that the inverse of f of y is equal to the cube root of y minus 1, which implies that the inverse of f of x is equal to the cube root of x minus 1. Now it's really important that we don't forget to express our final answer in terms of x again. Now we were given it in terms of x, so the inverse function also has to be in terms of x. Now if we just have a wee look at what the graph does here, this is the original graph, x cubed plus 1, and if we now look at the inverse function, that's the graph of the inverse there, and you'll notice those are symmetrical. And they're actually symmetrical across this line here, and that's the line y equals x. Now we'll come back to looking at the graphs in further depth in the next lesson, but I just thought it would be good for you to see that just now as well. So I would pause the video at the moment and copy this down in your notes jotter. Now, I did say we would go through a second method for this. So, remember I said earlier that if f and g were inverses of each other, then f of g of x was equal to x. So if we know that we've got f and the inverse of f, then f of the inverse of f of x must be equal to x. So everywhere there is an x in f of x, so there's only one x here, we are going to replace it with the inverse of f of x. So we have the inverse of f of x all cubed plus 1 equals x. Now I want to rearrange that. I'm trying to find a formula for the inverse function here. So I can see it's here, so I need to isolate that. So I'm subtracting 1 from both sides. So the inverse of f of x all cubed is equal to x minus 1. And then I need to cube root both sides so that I get the inverse of f of x is equal to the cube root of x minus 1. And that is my final answer, and it's also the answer I got using the other method. So both methods are valid, but you need all of the working that I have stated in both methods in order to get all of the marks from the SQA. So again folks, I would copy this down in your notes. Now let's look at a second example. We've got f of x equals 2 over 1 minus x, and g of x equals 1 minus 2 over x. And we're told that x can't be equal to 0 or 1. So that's the domain, and it can't be equal to 1, because if it was, this would be dividing by 0, we can't do that. And likewise here, if this was 0, we would be dividing by 0, again we can't do that. Now firstly we're asked to find f of g of x, And secondly, we're asked to find the connection between f and g. So f of g of x then, so everywhere in f, where there's an x, we're going to replace it with g of x, which is 1 minus 2x. So here's f here, and everywhere there's an x, we're replacing it with 1 minus 2x, like so. Now, if we look at this denominator here, we can simplify that. So we've got 1 minus 1, that gives me 0, and then I've got this negative multiplied by negative 2 over x, so that gives me positive 2 over x on the denominator. It's 2 divided by 2 over x. Now if I multiply both numerator and denominator of the bigger fraction, if you like, by x, that leaves me with 2x over 2. It eliminates the fraction within the fraction, and I am left with x there. So I've found f of g of x, that's equal to x, and stating the connection between f and g, well, because f of g of x is equal to x, that means f and g are inverses of each other. So the inverse of f is equal to g, and the inverse f is equal to the inverse of g, vice versa. Now again, folks, we can have a wee look at that graph here. So firstly, the green is the graph of f of x, and the blue is the graph of g of x, and you can see that those are symmetrical across the line y equals x. Again, there's space in your notes for you to copy this down.